everybody. My name is David Nygren and I'm the founder of LENR-Forum. Today we have a lot of guests, very interesting guests, and Ruby will present them later in a few minutes. Today we will speak about lattice energy conversion symposium, and we will have about 60 minutes for this episode. So if you take over, Ruby.
Oh, thanks, David. We got a great panel to discuss the presentation of the lattice energy converter experiment. We have with us today Jean-Paul Biberian. We have Fabrice David. Is he here? Oh, Fabrice is not here. Andrew Erickson. Alan Goldwater. David J. Nagel. And the moderator of our discussion, LENR-Forum's Alan Smith.
Hi, everyone. Okay, do you want to hand over now, Ruby? We can begin. By now, everybody should have seen the video that Frank and Harper have made. And by the way, we mustn't forget Frank and Harper, yeah, who are sitting quietly there.
Yeah.
And who are the inventors and developers of what they call the lattice energy converter. And this is an incredibly simple device, which has been replicated by a number of people here, tested by others, with varying degrees of success. Yeah, but in general, it seems to be a very reliable and accessible device. Yeah, which produces voltage and current, not huge amounts of current. We're talking millivolts, in perhaps several hundred millivolts, and a milliamp or so. Yeah, but the fact is that this device, it shouldn't work at all. But in my experience in the lab, it's been worryingly reliable, and does not really require any exotic materials and so on. There have been questions actually, and it's our intention to talk about them. And David Nagel was the first person to get back to me with a question, and I wondered, do you want to kick off by asking your question about the LEC, David? Or I can read it for you. Unmute your mic.
Thank you. You can read it if you would, please.
Okay, fine. Well, David answered like a good scientist. His question is not just a yes or no question. It's a little more involved. His question is, do nuclear reactions cause the operation of the lattice energy converter? In other words, are we looking at a nuclear phenomenon? And how is that verified experimentally? Yeah, and there is a rider as well. If that is deemed to be, true, what does it say about the relationship between the lattice energy converter and the many other LENR systems that have been demonstrated, going way back to, of course, to Fleischmann and Pons, yeah, who weren't looking for electricity, I know, but nevertheless, how does it fit into the family of known LENR devices? But first of all, the radiation question. Perhaps Andrew would like to answer that one.
I've been working with Frank and Harper for over a year now, trying to answer that question, because I think it's one of the fundamental things that would help put a nail in some of the coffins, if you will. I don't have the same level of fidelity instrumentation that David Nagel has, but I do have a silicon photodiode used for X-ray fluorescence. I recently put together a cloud chamber to look at the operation of the cells. I have yet to see convincing, I will say, evidence of radiation after running cells, but I also can't say at the moment that it's been ruled out. So, you know, I'm continuing the search on that because I think the cell is interesting regardless of the phenomenology, but understanding whether it's there's a nuclear process involved is something that I'm very, very keen to understand and ascertain.
Mute. Would anybody like to add anything to Andrew's response there? I mean, perhaps Jean-Paul, have you looked for radiation?
I didn't really look for radiation. I checked. I mean, I have a Geiger counter in my lab, but nothing happened there. So I'm not sure there is anything coming out from there. I looked at the effect of magnetic fields. Couldn't see anything convincing there. I tried temperature changes for production of voltage and current, but not for radiation, really. I tried putting some radioactive materials on it, like uranium. I have pieces of uranium. Didn't see any change with that too, so I don't know. I don't know about that. I don't know more than that.
Okay, so I think it's going to be down to you, David, to get your sophisticated machinery, David Nagel, to get your sophisticated gear to work on that one. I too have put a Ludlam pancake detector onto a working electrode and saw nothing. Yeah.
So I am just beginning to make runs with this cadmium telluride detector. That's good up to about 150 keV. And first one yesterday basically looked like noise, but it's too early to say anything. Let me ask John Paul, if you did magnetic field tests, I would appreciate knowing more about it. You know, what was the configuration of the magnets, the rough magnetic field strength, and so forth?
Well, it's first of all, I'm using a 35 millimeter tube in which there are two coaxial cylinders, which are the two electrodes. And on top of that, I placed a magnet to about half of Tesla power, a very powerful magnet. But I didn't see any change. I didn't do a very detailed experiment of that. That will be necessary to be done in the future. But I just tried it like that to see if something was happening, and nothing happened. So that's not a proof that magnets are not sensitive. But I have to do more work on that in that direction too.
Okay, thank you, Jean-Paul. Maybe yes, maybe Frank and Harper have got something to add to this.
Microphone?
You have to unmute.
Okay, can you hear me now?
Yeah.
Okay.
Yeah.
This is something that we have talked about numerous times, and so let's go back to the basics. Something's ionizing the gas. I believe if we're conducting current, if we're producing a voltage and current, something has to be ionizing the gas. And we have racked our brains being a mechanical engineer. I've been trying to think, are there non-nuclear ways to do this? Right now, we suspect that LENR is involved, but we really don't know. So this is a question we would like to have answered, but at this point, we don't know. Don't you?
Okay. Well, I do like a mystery, so we still have a mystery. Yeah. Just if I might go back to John Paul for a moment, you asked a question in an email to me recently. It works in air. Does it work in air? You asked. Not hydrogen, just in air. And for my part in the lab, yes, it works in air, but not for very long. Yeah. Maybe for a few hours. Yeah. Or 24 hours at the most. But I know you've had success in hydrogen. Do you want to tell us a little bit about your results so far? I think you're muted again.
But you want to talk to who? To Frank?
Uh,
Or to me?
well, now I wondered if you have done some work on this,
Oh,
yeah? Maybe you could tell us just very briefly something about the results you've had.
Frank. Myself, I've done some experiments. I will tell you what I've done. Whenever I am under vacuum, there's no voltage under vacuum. Now, when I put hydrogen, there is voltage. I have, in the very beginning, there was a leak, and I was checking for the leak with acetone and alcohol. And the voltage was huge when I was putting alcohol or acetone. That's very interesting. So I don't know why acetone is so good. There is a lot of hydrogen in acetone for sure, but it's not really the hydrogen itself, because you cannot break the molecule like that. So something else, some other molecules might work. I don't know about water, or it's difficult to do. I mean, hydrogen is easy to fill because it's a gas. Other molecules will condense, so it's a bit harder. But that should be looked at anyway, I think, other gases.
I think Frank probably knows this work better than me, but J.J. Thompson did some work with various solvents, I believe, yeah, things like acetone and alcohol back in 1906 or whenever it was, yeah, and he discovered various effects, but I'm not sure about that. I'm running from memory. Yes, Andrew, did you?
I just wanted to also chime in. I've run a lot of cells in air. They work very well, but they have a short life. But in hydrogen, even at atmospheric or filled at atmospheric, but run at elevated temperatures for a while, that they last weeks to months. I just wanted to chime in on the success.
No, thank you. I did have a question for Frank and Harper, which was on longevity. We covered this briefly in a previous chat, but on the longevity of the LEC. And my question was, how long has your oldest cell been producing output?
You want to take that one, Harper?
Yeah, so we have a cell which we jokingly refer to as the bunny.
The Energizer Bunny.
And it is a palladium deuterium cell, because it was one of our early cells that we've made, and it is currently in operation. I have checked the voltage this morning, and it's been in operation in excess of 7 years.
Wow.
It is not a LEC. In that case, we are actually applying a voltage between the counter electrode and the working electrode, and it's measuring the conduction. So it has operated for a long time. The other thing I guess I would point out about air is Johnson Matthey makes devices that purify hydrogen out of air, and hydrogen is about 0.5% of the makeup of natural air, which doesn't sound like much, but it's sure enough to cause hydrogen embrittlement and problems. So the cells that have lasted longest, and this is, I don't know that I have any real proof of this, but when I've used the iron pipe and maybe co-deposited a little bit of iron onto the iron pipe and then palladium over the top, those seem to last longer, and it could be the iron loads up a lot of hydrogen, and so it's coming out. But I would point out here, even if what we're seeing here is the diffusion of hydrogen out, based on what I've read, the current theory is that hydrogen will come to the surface where it will sit, find a mate, and then drift off as H2, and so that model is probably incomplete because that does not produce any ionization.
That's quite right. I think it might be a good idea to ask Alan Goldwater, who's had some difficulties with replication, if I can say so, but maybe you could tell us a little bit about what you've been trying, Alan, and the difficulties you've had.
My attempts have been using plating iron onto brass active electrodes, and it took several attempts to come up with the chemistry to form a robust, durable iron coat. Typically, they would peel off or form a rough surface, and in those cases, you get galvanic shorts inside the cell that produce a false positive. But with the right chemistry and careful control of the plating current, you can get a nice smooth iron layer. Evolution of hydrogen is pretty well shown by foam or bubbling on the surface of the electrolyte, and also using a combustible gas detector. So I know that I have co-deposited iron and hydrogen. I've also done some work with adding deuterium to these cells, but in none of the cases have I found a convincingly active cell. I had a couple of false positives, and those were related to the measurement difficulty at high impedances. But I think it's possible that plating with only iron would produce an effect, although from what I've heard so far today, following that with a layer of palladium is really the way to go. I'll need to get some palladium chloride and try that in my next series of tests.
I would just mention, by the way, that cadmium as an overplating might be an interesting material, because cadmium forms a perfectly good hydrogen barrier. They use it, they cadmium plate the inside of those big hydrogen storage tanks just to help reduce the chances of embrittlement. Yeah, so it may
You're
be
suggesting CAD over the iron?
CAD over the iron. Yes, yeah. I haven't tried it, but it's a possibility.
Before we go, excuse me.
Yes, David.
If it's timely, let me ask Frank to describe the preparation of the LEC that he sent me. It arrived last Friday. I don't know if you can see it, but this is a micrograph I took yesterday of the surface that shows both rust-colored and black-colored spots, many of which are remarkably circular, surprisingly circular. So I was able to get good results of 4/10 of a volt to 5/10 to half a volt over many hours. I did the resistance curves, and as I just said, I'm starting to do the radiation measurements now. So anyway, Frank, if you could describe what was done to prepare that LEC, which worked in air right out of the box and is a stable voltage source.
Unmute.
My wife would like one of these switches, I think. That electrode started out as a 1/8 inch by 4 inch iron pipe, black iron pipe. And it had a coating on it that I sanded off with my sander. You know, the coating was to prevent rust. So I sanded that off and then co-deposited some iron on it, a layer of iron from, and I've used two iron deposits. One is the method that De Stefano worked in Italy or Sicily, where he actually just used an iron rod and what was the
Muriatic acid.
Muriatic acid or
That's right.
swimming pool acid. The other I've done is I've got some iron chloride that I mix in and have used that to deposit iron. That will rust very quickly in the atmosphere, and so I've tested it and it rusts. So I then put a layer of palladium on it, and the features that Dave showed were not there when I first prepared it. When I first prepared it, it was that your typical palladium coating, and then after testing it, we see some of these volcanic-like features that are red in the center, which are orange in the center, which looks like rust. And I don't know what caused those. I've read that when you deposit iron, you can trap some water. And I thought, well, if I heated the electrode up, that could have caused the water to turn into steam and maybe create one of the, fracture and create one of those features. But that electrode, I don't think has been heated up to the temperature that would have done that. So I don't know, but we have seen those features before. And in fact, a picture of that is in the paper, the second paper that we've submitted. It's John Paul sent it back to us with the reviewers' comments. We made the changes and then actually added a couple of appendices to the paper because of the questions we were getting about the analysis. And that's now I returned that a few weeks ago to have it reviewed again and hopefully approved for publication. But there is a picture that's similar to what Dave just showed.
Okay. Does it like with only a palladium deposit work, that is without the iron deposit?
Yes. In fact, Dave sent me an email last night or early this morning that he's thinking about using a copper tube like we use here to connect your water line to your refrigerators for ice maker. That was actually what we used for most of our early experiments. Was we had that copper tube. We could plate palladium on it. We also did experiments where we plated a nickel flash on the copper tube and then deposited the palladium on that. We've also deposited silver on the copper and then palladium on that. The electrochemist could probably say why some of those might work better for plating, but we've done that. Do you want?
Yeah, I wanted to make a comment. The cell that's been running for the 7 years is copper and palladium and deuterium. That's the one that's been running.
Okay.
There's 2 electrodes that are brass, nickel flash, and palladium, both put out in excess of 500 millivolts in air.
That's right. Yeah, I've just used brass and iron. I'm plating onto brass sheets so far, and I haven't had excess of 500 millivolts, but I've certainly had close to it, 450, 400, and so on. On the topic of materials, by the way, I would like to ask Frank and Harper if they have found much relationship between the work function of the metal that they use for the electrodes, and I'm thinking about, silver versus copper or zinc or whatever for the base metal. Have you found this makes any difference?
Don't you?
Well, my feeling is that zinc makes a good counter electrode. There have been 2 studies, both of them quite old, where they have looked at work function effects and various combinations of metal. Kramer's study back in 1928 and Omott's study in the 50s. And they've published a rather nice table of materials that they tried, and zinc was one of the better ones for the counter electrode, and I'm not sure, but I also think that it might that there may be some photoelectric effect taking place, so that the radiation is enhanced by a nice low work function counter electrode.
Right, I did suspect that was the case. By the way, I must welcome Fabrice David, who's joined us, also from France, and hi Fabrice. And I know he's worked on what you might call a precursor or a kissing cousin of the LEC himself, with Charlie Enterman. I'm sorry you've missed most of the discussion, Fabrice. Do you have any questions for Frank and Harper? You'll have to unmute. It's very low bandwidth. Unmute your microphone, David. Top right-hand corner of your screen somewhere. I can't do it for you, I'm afraid. No.
Yeah. Sorry.
That's it. We have you.
Okay.
Right. So, David, do you have any questions for Frank and Harper?
No.
Mhm.
I think that the result of Frank and Harper are probably the most important result in the field of direct conversion. So I am very happy to be a member of this discussion.
Mhm. So far, I was just going to say, so far we have covered topics like the measurement of radiation, right? None found so far, yeah, but that's an ongoing project. We've also talked about plating materials and the longevity. And you may not know, but Frank and Harper have had an early prototype cell of a slightly different type to the current LEC, which has been working for 7 years. It's a long time. Yeah, but carry on, please, if you want to know anything else.
Let me clarify.
No,
Are we on?
Yeah, we're unmuted.
Okay, well, let me clarify one thing with regard to the longevity. I am referring to the longevity of the working electrode. I
Yeah.
believe that in the 7 years we have had 2 deuterium gas replacements where we have regassed the cell.
Mhm. Okay, I think that's allowed.
Wait, did you change deuterium because there was a leak or because you wanted to clean up the chamber?
The phenomenon that we have observed is rather unusual. Again, in this field, we have a pressure measurement on the cell. We have it's running continuously with gauge pressure being monitored. And we find that over time, we tend to lose pressure. One would anticipate that this might be a leak. However, if you let the cell continue to run, it will then go to negative pressure and the cell continues to operate even though we're now below gauge pressure. So, I mean, we're in terms of absolute pressure, we have absolute pressure in the cell, but gauge pressure is negative. It's awfully difficult to ascribe a leak to the sustaining a negative gauge pressure.
Well, it is
So
possible.
it appears, at least from the observations that we've made, that we are actually consuming the deuterium.
What kind of gauge are you using?
It's an inexpensive compound gauge. It goes from minus 30 inches to plus 3
So
bar.
it's a mechanical. It's not.
Yes,
mechanical.
Yeah, right.
Well, I mean, you can go below atmospheric pressure if you have very small leaks. That means hydrogen can go out, but the oxygen cannot go in. You know, that happens sometimes. I had this experience in the past, so I'm not sure it's a consumption of hydrogen. Could be a leak anyway, because the partial pressures of hydrogen inside the chamber and in the air is not the same. It's a partial pressure equilibrium. It could be, I'm not sure. Microphone, Alan.
Thank you. There it is. That's it. A diffusion phenomenon is possible. Yeah, where the deuterium is diffusing through the metal. Yeah, this can happen, and you will get below gauge pressure that way.
Yeah,
because yeah, it's the rule of partial pressures, I believe. Yes, takes me back to school, right? And are there any more questions? Because I think we should be winding up soon.
yeah.
Yes, Andrew.
Just real quick, one of the things that I've been looking at is sort of elevated temperature plasma processing. I think everybody that's run one of these cells that elevated the temperature has seen an output increase substantially with temperature. But I'd like to open that one up a little bit if we have a minute or two to discuss temperature effects.
Of course. Yeah.
Well, I have done it, and I have seen a voltage change with temperature. And as the temperature goes up, the voltage goes up too. So, but I didn't do any detailed experiment, but I've seen it definitely.
Mm-hmm. I think also Frank and Harper have done some work at higher temperatures.
Yeah, we're unmuted.
We've run several tests. We have a kiln, and we put the cell in the kiln and run the temperature up. And we've gone up to around 200 degrees C. And in at least one of the experiments, I did some calculations and found that a good fit is an Arrhenius curve. It seems to be very nice, and the amount of increase in performance is directly related, as you would find with the predicted number of vacancies if you compared the voltage current plot against normal metallurgy prediction. They both fall on an Arrhenius plot.
Mm-hmm. Okay. David Nagel.
Regarding temperature, if I build the LEC, I'm going to have a hollow working electrode into which I can put a cartridge heater with a thermocouple in order to be able to change the temperature of the working electrode. To change the subject, we've talked about radiation, and of course radiation includes photons, includes electrons, includes ions, and the generation of photons and then their absorption is one thing, but if you emit charged particles, electrons or ions from a working electrode, then you are moving charge directly. Okay, so I should remember this, but I don't. Frank and Harper, the working electrode becomes charged which way, negative or positive?
Yes.
Yes.
That's a loaded question.
Yeah, you can see why I'm asking. I mean, if it's one way or the other, then that's either that implies electrons are leaving or ions are leaving. So one of my interests right now is moving it. If you have a working electrode here and can move another electrode near it to pick up electron emission. Has anyone done that yet?
No.
Okay.
No.
Yeah.
John Paul, you've seen the change in polarity.
Yeah, I've seen a change of polarity with temperature. So there's something going on with temperature. So maybe it's just the work function is changing. It's a possibility. I don't know about the work function versus temperature. And the work function is a global measurement, so it's not local. So if you have micro tips at the surface, maybe the emission will be different of bulk material. Maybe there are some changes due to the granulometry of the surface. Has anyone done any AFM type measurements so you can see at the atomic level what the roughness of the surface is? AFM would be good for that.
Mm-hmm. I have done a little bit of work myself on barriers between working and counter electrode. Once again, only very quick experiments in air. And I found that actually the stuff that used in America as fly screen for windows makes a good physical barrier for low temperature experiments. And if you want to get hotter, Teflon coated glass fiber mesh, the kind of stuff they sell as for barbecues, for putting on barbecues, also an excellent separator. Both of those seem to allow plenty of current to, plenty of the mystery force, the ions or whatever, to go across between electrodes, and you get a good current. However, when I try a piece of paper, a piece of dry, ordinary printer paper, then the voltage is very much reduced. And if you put a very thin layer of plastic, I used cling film, saran wrap, and that also cuts transmission totally. Nothing. You get 0 volts there. Yeah. So it would seem that the greater the surface area exposure between and the closer the distance between working electrode and counter electrode, the bigger you get a bigger bang. Yeah, it works better. Yeah, but that may seem obvious, but I just think it's worth mentioning. Yeah.
Well, one of
Okay.
the possibilities, of course, is to take a counter electrode that's a cylinder that can be moved along the length of the working electrode to measure the non-uniformity of the working electrode. And you know, if a person could get a signal with, say, a centimeter long cylinder, then you go to a millimeter, you know, and see how much variation we can measure along the working electrode. That's not hard to do.
No, if it's anything like the co-deposition experiments of Stan Spack and co, it may well be that there are hotspots as well, which it could detect. Yes. Yeah. I think we can take one more question, and then we really must bring this very good discussion to a close. Yeah. Is anybody else?
I have a question. You know, when I started the experiments, I had palladium bromide, not chloride. So I started with palladium bromide. It was not supposed to work, but it worked. Since then, I tried palladium chloride, and I was not successful at all in doing the deposit. So has anyone the recipes I could use about the preparation of the surface of the electrode, and then the exact concentration of palladium chloride and chloric acid or whatever you put in, and time and current? Be interesting to have that for me.
Okay, I can certainly send you the iron plating recipe that I used, which is from about the 1880s or something like that. But it seems to work okay. It still works, but it does need to be fresh, I think. And Alan Goldwater, then this must be the last.
All right, I just wanted to add a few comments from my experience in plating of iron. The chemistry that Alan Smith suggested worked pretty well for me, but I found that it traps quite a bit of water beneath the iron coating or intercalated with it. My tests are done in a vacuum chamber, so I can tell when I'm pumping it down whether there's any entrapped materials, and it took quite a long time to pump down because of all the water vapor escaping, and that sometimes also causes the plating layer to escape. I also do monitor with an X123 X-ray spectrometer, and I saw nothing above background in any of the tests that I did. I've tried both hydrogen and deuterium, and so far have not produced a convincingly active cell. But the plating itself is a tricky part. So you must watch for the evolution of water vapor, and that's a potential source of galvanic voltage in the cell. And so these are some tricky things to sort out to make a cell convincingly active. False positives are really a risk with these, in my experience. And that's about all I can add at this point. Thank you. And thanks to everybody for participating. My work is all in a document that I'll circulate after the event is over.
Thank you, Alan. Thank you very much. And a final word perhaps from Frank and Harper. What's next?
Well, I want to thank everyone for participating. And as far as the co-deposition, there seems to be a broad range of what will work and what won't work. And the same thing you did one day may not work as well the next day. I go back to the paper that Rout and Srinivasan and others published in Bark, and there are several papers there where they were doing experiments, and they could fog film with the electrode, but they could not detect it with any of their sensitive instruments. And so we've talked about what is that telling us. This is one reason we came up with the idea of maybe what we have here is a counter electrode and the photoelectric effect, but you still maybe should detect the energy. So bottom line is, I think the plating and preparation of the electrode is going to be critical. And in the presentation, we mentioned different metallurgy and different ways to prepare the electrode, which they talked about briefly in the Bark paper, but I think they used vapor deposition and maybe a couple other techniques which worked. And so if vacancies are important, we know you get vacancies with co-deposition. Fukai said that. So if they're important, is there a way to produce a cell with known vacancies in known locations with different preparation techniques? And that's beyond my knowledge at this point, but that's a working question.
I'd like to make a closing comment, since I've been poring over the mathematics of how the cell works. And the rather remarkable feature that I have discovered is that in the last 120 years, there have only been 3 people who have investigated the question of how conduction of electricity in an ionized gas takes place, including diffusion of the gas. And when I look at the mathematics, I find that I have a difference term. The difference term depends upon the mobility of the positive and the negative ions. And so the most promising thing that I can think of as an experiment that needs to be conducted is to make essentially a penning gas mixture where we add a neutral molecule like a xenon to the gas, where we have a nice difference in mobility, because that then will enter into the diffusion coefficient via the Einstein relationship, and that should enhance the performance because it will separate the fast moving ions from the slow moving ions.
Yep, thank you. Oh, thank you, everybody. I'm going to hand back to Ruby in a moment, if she is. Yeah, unmute, Ruby.
Unmute.
That is all the time we have. Obviously, this discussion will go on. I hope we'll have another meeting, another little symposium, and we'll get some updates on your upcoming experiments. The direct conversion into electricity is one of the most important things that could come out of LENR. So I hope we'll be hearing more at the big conference too. And David, thank you for hosting this event.
Thank you, everybody. It was very nice to see you all here, and we will post this on YouTube, and you will find the link in the description down here. You can also find more information over at LENR-Forum. There we have a dedicated page of this experiment. So thank you very much, everybody.
Yes, thank you, everyone. It's been real good fun, actually. I loved it.
Appreciate it.
Thank you.
Good night. Good day.